Okay, hello. So this video we're going to be doing CSM 61C Fall 2019 Problem 3 on Worksheet 9, which is virtual memory. This problem is called context switch, so you can probably guess that we're going to be doing something similar to doing something with context switches. So for context switches, what this basically means that in the TLB, which is also called the translation look-aside buffer, in this thing we're going to end up flushing or basically setting everything into invalid to make sure that when we do a context switch from one process to the other, it sets up correctly for the other process, or it refreshes for the other process. So in this question, I'll let you read just the top part while I'm talking. But the key things to note are that there are 4 kilobyte pages, 1 megabyte for virtual address space, and 1 gigabyte for the physical address space. And then there's a single TLB that stores 4 entries, so that's super important for later. And then also we may assume that the TLB is fully associative, and then LRU replacement. So LRU stands for least recently used, which means that the least recent thing that has been used, if we need to kick something out, that thing will be kicked out. And then a TLB entry is shown below. So a TLB is something you check before the page table, and is usually something you check right beforehand, and it's very, very similar to a cache. How it caches memory, but it's how a cache caches memory. But for us, we're gonna cache page tables or page entry, like page mappings, similar to what the page table does. Except this one's gonna give you the valid bit to tell you whether or not it's valid or not. Permission bits to see depending on maybe if you're the kernel or user, which is again something that's not covered that much in this class. But don't worry about this. But there is something called permission bits that you need. LRU bits helps depict whether or not you are like the least recently used thing, or you were the thing that was just recently used. So that's just telling you how to like kick something out. You check the LRU bits, and then obviously you have the virtual page number mapping to the physical page number. So let's get straight into this problem. For part A, it's asking, given a virtual address, how many bits are used for the virtual page number and offset? And just like what we've had before, there's in the video from before, we know that number of bits for the VPN. So VPN, I'm not going to be too specific because there are things in the past video. VPN bits is equal to the total virtual address bits minus the offset bits. Oops, my bad. And we know that the total virtual address bits. So, and then PPN, which is physical page number, is also equal to total physical address space minus offset bits. And we know that offset bits is equal to log base 2 of page size. Alright, and in this, like the problem that gave us, page size we know is 4 kilobytes, which is 2 to the 12. So 4 kilobytes is equal to 2 to 12 bytes. And that means that offset has a total of, I think 12 bits. Now, if we look at VPN is equal to total virtual address, which is 1 megabyte. A reminder that megabyte means 2 to the 20. So we know that there are 20 bits there, and then the offset is 12 bits, so you know I have 8 bits here. Then physical page number is 1 gigabyte, which is 1 to the 30, so 30 minus 2 to the 30, my bad, which is minus 30 minus 12, which gives you 12. And that means that with this, we know exactly what we need. And over here, we know that the VPN has a total of 8 bits, while the offset is equal to 12 bits. And for over here, the physical page number is, I guess my notation's a little bit different, is, I think I did something here. Yeah, I made a mistake here. This is 18. So, their PPN is 18 bits, while the offset is 12. So something to note, because it is very important and crucial, is that the offset bits, you can notice here, they're asked for what is the physical page number and offset, and this is the virtual page number and offset. And what's very important here is that the offset is exactly the same. They didn't tell us how many pages how big the physical page was versus the virtual page. And the reason why is because the pages for both virtual and physical are the exact same. So that is why the offset bits for both of these are the exact same as well. Yeah, so this is something that's very commonly asked in questions on midterms and also just any random questions. They will usually give you some information and ask you to solve for some bits or ask you to solve for how many pages are existing. But if you are given most of this, it should be just, if you have this on your cheat sheet, you're good to go. Now looking at the next problem. Oh no. Okay, so this is something I recommend if you just have the worksheet, look through first. I'm gonna give you like, feel free to pause the video because I'm just gonna assume that you've already looked at it in the next few minutes. But also make sure that, or if you pause the video to watch it, that's cool too. And then there's also this part right afterwards as the actual question. So again, I recommend just going to the website and getting the worksheet and or simply pausing the video and reading it. But I'm going to assume that you already read it. So now we're going to start in part A. So part A is asking about the TLB hit rate for executing the code above, and then assuming that TLB starts out cold. And then make sure you consider access to data and ignore any effects of fetching. So don't worry about anything other than like knowing that you're accessing. You may assume I, J, and X are stored in registers, so we don't need a memory access for those. And we have to flush the TLB on a context switch from one process to the other. So that is very important. We want to make sure that we know that whenever you context switch, your TLB ends up getting flushed. So now let's look through what's given to us. We know that whenever you're looking for some memory and you want to access some virtual address to physical address, when you don't have something, you are going to end up being like you're going to end up getting some page of information. So we're going to look at this code, and you can see how in this code, at most, the distance we go from any location of any like address, you can see for A, we go 0 to, I'm assuming only up to time 8, whatever this time, 8 seconds, 8 nanoseconds, not sure, but time 8, the most we go for A, it goes from I, which I represents 0 in the beginning, to 192. So that's something that that's all we need. For part B, we know that we go from, J starts at 0, and we're setting X to equal 256, but then we subtract 1. So we're going from at most 255, and then I think we're going minus 4, so I think it's 250 minus 3 more 2. And this is, again, what I wanted to notice, that this is all the memory we're looking at. So let's say, right, so that is something important, and you'll see why. But let's just start going in, right? So at A1, AI equals I. I is technically 0 at time 0, right? Because we're starting the for loop with I equals 0. So what we have is looking for A0. And this memory location, or this address, what we're going to set it to, we don't actually have yet, right? Because our page table, our TLB has a total of 4 entries. But we have there's also like a whole bunch of bits here, but I'm not going to worry about those. The point is that, actually, no, we do need to worry about those. Yeah. Let me redraw this thing so that it's a little bit bigger. So this is the TLB. We have some valid bit. We have some permission bits and stuff. I'm going to ignore everything else. Oops. And then let's say there are others, but from the top, but I don't think we need those for now. So this is our TLB. So this is entry 0, 1, 2, 3. And originally we're looking for something that has A0, right? That's going to be our first thing. We don't have it because it's obviously nothing here. So we're going to get a miss at first. And we're going to get the virtual page number of A0 and virtual page number of physical page number that contains A0. Now, aside here, I just want to mention is, if you look back on the page above, we know that actually each page is going to be 4 kilobytes. 4 kilobytes, again, is the same as 2 to the 12 bytes, which is plenty more, right? That's like 4,000 bytes. That's plenty more than how many bytes we're going to look at through all of these. So whenever we look at for any one of these pages, it's going to cover all of them. That's why I wanted to mention all of what we're going to see. But that's why you'll see me not label which physical page number or virtual page number. It's because it's going to be the same one for A, and then for B, it's going to be that same one. So we're going to look at this. We're going to miss. And then for the next one, so A0 is going to be a miss, right? And then we're going to try to do A1, because right here it says not A1. A64, right? And that's going to be a hit because of the fact that, permission, I don't know what's going to be here, but it's fine. Don't worry about it. Yeah. So the main thing that it is valid, right? Because we just pulled this in, and now it's valid, so we're going to get a hit here. So everything is fine here, and it's like, nice. Now, what's going to happen is we're going to flush this out, because anytime we have a context switch, we're going to flush this out. So now, what happens when we flush is we basically kick it all out, or the other option is to set the valid bit to 0. Right, so that's what could happen whenever we flush something out. And now we're going to be looking at this one. So for this one, we're doing no information, so it doesn't matter. But over here, we're getting B of 255. And this is going to be a miss. And the reason why is because we have nothing here that has anything to do with B. So we still have to pull in a block that has to do with B. So for this, what you want to remember is that for a page, you're not pulling it starting from a certain index. A page, starting from a certain offset. A page has a built-in from 0 to something, or they have these boundaries, right? So when you pull something in, they come in that boundary set. So you don't start from 255 onwards for 4 kilobytes. It's actually most likely going to be something from 0 to 4 kilobytes. So that's why you can see me writing here, it's B0. And what I want to note is this B0 is going to be the same as B block byte 0 all the way to byte 2 to the 12 minus 1. Something similar along the lines of that. But the main thing is that it covers up. It includes what you need here. So it's similar to caching again. And what we're going to do here is we're going to set something here. But then the main thing is we're going to have 1 for valid bit here. And then now we're going to look for 254. And that's going to be a hit, right? Because we have that block. It's valid and it works. So what's going to happen next time, right? We just finished this one right now. Now we're going to go to this one. And we're going to look for I think that's 128. And this one, you'll think, right? Some people are going to draw this and be like, wow, we have that, right? VPN A0, which again, just like I said before, has A0 all the way to A2 to 12 minus 1. And you think, wow, we have that. However, you got to remember that we actually ended up taking away this, right? So this right now actually has valid bit 0. So it's actually not valid. So we have this technically in the TLB, but it's not valid, so we can't use it. So sadly for us, we're going to actually have to miss the first one, and then only then do we set the valid bit back to 1. And then A192 is going to be a hit. So sad, but we actually don't have the ability to count that as true. And also, what I completely forgot to mention is when we switched context from process 1 to process 0, I forgot to change this valid bit to 0, right? Because technically from process 1 to process 0, that's also the same thing as a context switch. So when we finished B254, we actually ended up setting this to 0. And now, again, process 0 to process 1, lucky us, but valid bit's going to be set to 0. And then only now are we going to be able to, technically we're going to miss this one because of the fact, so B, it's going to be a little bit messy, but 253, it's going to be a miss because of the fact that originally it was valid bit 0. right? And then now we're gonna miss here, and then set to 1, and then we're gonna look for B252. That's gonna be a hit, and then that's when we have the ability here. So we just finished this thing, and now we've looked through everything, and you can see how for basically every single one of these, it's the miss hit, then a miss hit, then a miss hit, then a miss hit. And the reason why for time 2, this thing was ignored was because this isn't accessing any memory, right? X and J, they said, are assume that these are stored in registers and therefore do not need memory access. So what we can see here is that we got a miss for this one, then we hit because we stored it, then we context switched and we set the valid bit here to 0, and then we moved over here. This does not need anything. This is a miss because we never had a B block. Then we hit. Then when we context switch over, we set basically both of these all have valid bits of nothing. And then now we're going to miss here again because we set the valid bit to nothing. Only after time 5 do we set it to 1, and then we hit here. And then we switch context processes again. And then if you remember correctly, when we went from process 1 to process 0, we actually set this to valid bit to 0, so now we're going to miss again, then we can hit. So, and we have these hits in because of the fact that the blocks that they come in, as I said from down here, are the same blocks, or the same pages. So whenever you miss one of them and you pull a page, the next one is still within that page, so you're going to hit. So you can see how we have 4 misses, 4 hits, which means we have a 50% hit rate. Right? Yeah, wait. What is the hit rate? Yeah. So, time to do next question. For 3.3, we have 2 problems. Wait. That's weird. So I think that on the worksheet, we only have up to we only have A and C, so I will not be covering part B. But for 3.3, let's just continue on. 3.3. So now what we're going to do instead, right, because as you can see, the hit rate was 50%, even though we were basically using the same block whenever we switch processes. So let's think about a way, well, maybe, why don't we keep a way to make it so that the address space ID, ASID, here, identifies virtual space for each process. So now, whenever we have the VPN and the ASID, then we're good. Like, we don't need to flush it out. Like, it doesn't, like, we don't need to worry about flushing and then not having these context switches mess up our hit rate. So, if we think about back here again, what's going to happen for time 038, assuming it starts out cold? So, what's going to happen? What's going to happen here? So, ignoring, I'm going to have, what I'm going to have is the valid bit and then the ASID, because as you saw earlier, okay, that's ASID. And what you saw earlier was we never used a permission, so I'm just not going to keep it. But basically now we're going to be doing VPN to BPN, and let's go back up top. So we know that, oh, oops, my bad. We know that so far, ignore these blue lines, that we have A1, and let's say we missed that one, right? Because as you saw, we didn't really have it. So we're going to get the VPN for A0 and the PPN for A0. Oops. And then we're going to set this to valid, and then we're going to get, oh, why can't I draw anymore? Okay. Oh, okay. So ignore these, ignore these, ignore these, and ignore these. So we know that the first one we're going to miss because of the fact that obviously we started out cold and we have nothing. And now this thing is going to match, let's say, process 0. Now, let's go over here, and we're going to look for that A page, and that A page is going to exist, right? We just pulled it in. So, of course, we're going to hit here. Now, what about this one? We're going to do a context switch, but as you saw earlier, valid bit might be set to 0, but this ASID is going to stay here. So, or like something will get flushed, but no matter what, this ASID and VPN will stay here. Now we're going to go to process 1, and this thing, again, does not access any memory, so we don't need to worry about it. But bx minus 1 equals j, this one we do, right? Bx minus 1 is going to access memory. So looking at this problem, we're going to get set valid bit to 1, process to 1, VPN of B0, PPN of B0, and this is going to be a miss first, and then we're going to hit here. And then we're going to get a context switch, which again, maybe valid bit is set to 0, but again, I really don't care, because all we care about for a hit is if ASID and VPN are there and they match. So let's go on to the context switch at time 5. We earlier context switched from 0 to 1, and now 1 to 0. So everything in our TLB, the valid bit is 0. Like, everything's been flushed out, technically. But we're going to look for the A page, and lucky for us, the ASID is process 0, so we actually have access to that. And it works, so everything's good. And what we can do here is we can just set this to hit, because we hit, right? We have this. ASID is 0, process 0, and VPN A page is here. Now what about this one? It's the exact same thing, right? We have both hits because of the fact that we have the ASID of 0 and VPN of the A block. Now we're going to context switch and go back to process 1. And as you can see, I don't really care, right? I have the ASID, I have VPN, and we are at process 1. So this B block exists, and the ASID is process 1, so we're going to hit here, and the same exact reasoning here. So looking at what we just did, we were actually able to make it so that out of the first 4, we got 50%, so 2 out of the first 4, and then also we got 4 out of the last 4. So that means we got a total of 6 out of 8, which is 75%. So because of this ASID, it turned out super better, and now it's a lot better like time, like hit rate time. Yeah, so I think on the worksheet we only have part C, so I've never seen part B, so I will maybe talk to anyone who wants to message me for it, but this is part C. Let's look at part C, and it says found in part 4, but I think I think that's a small typo. I think it's just asking for this one right here. If not, it might be part B, because no. Yeah, so 3.1 had 2 questions, 3.2 had 1 question. So I think part 4 is this thing. So looking at this problem, we want to know how many, what is the smallest number of TLBs so that we can still have the hit rate found in part 4. So if you look at this, and what I just did here, right? I don't know why I did that. We only used two entries in my TLB. So if you think about this, we only really need 2, right? Because as I showed you right here, we only need 2 places in my TLB, and our hit rate for part 3.3a, which is I think part 4, I'm not entirely sure, is going to be exactly it. So yeah. I think that is the last thing for question 3. Feel free to reach out and ask if you want a different question covered. And thank you.